Okay, thank you very much. And then next in line is our invited speaker, Alessandro Tarantino. Brief introduction from me. He's Professor of Experimental Geomechanics at the University of Strathclyde in Glasgow, Scotland. Current research interests include the direct measurement of water tension in soils and plants, micromechanical behavior of saturated and unsaturated clays, soil-plant atmosphere interactions, stability of natural engineered slopes subject to rainwater and floodwater infiltration. He has led major European consortium research projects, including the Marie Curie European Network TELE, and then co-editor of the books Advanced Experimental Unsaturated Soil Mechanics and Laboratory and Field Testing of Unsaturated Soils. He's been keynote team lecturers at numerous international conferences, including the 8th International Conference on Unsaturated Soils in 2023 and the ICE Geotechnical Lecture in October 2023. Without further ado, Alessandro, the floor is yours. Thank you.
Thank you, Michele. Thank you all first to stay until the last session here. Thanks Farima, Michele, and Marina for inviting me. Thanks Alessia, who is the co-author of the paper that you will have in the proceedings. So 5 points I'm going to touch: motivation and scope, historical barriers to undergraduate teaching, why teaching unsaturated at undergraduate level, what is convenient to start with, and how do we teach, which is sharing our personal experience. So the scope is turning towards undergraduate teaching, which means two things. Unsaturated soil introduced at the same time as saturated, and by non-specialist teachers, so those who are not carrying out research on the topic. Two challenges: use same language as saturated soils and be simple but not simplistic. What I'm not going to talk about is advanced unsaturated soil mechanics, but you have 3 nice presentations after me where you are attacking the problem on that side. Inspired by this paper, so this paper it was a first attempt to talk about teaching unsaturated soil mechanics from the perspective of a non-specialist, Marina in this case. Historical barriers. So when you have a saturated soil, you are defining a pore water pressure, you have an operational definition via measurement. The pore water pressure drives water seepage, controls mechanical behavior, we all know about that. You turn to unsaturated soil, you open the first textbook that was designed on that topic, still used as a reference. You are hearing about suction, drives water seepage, right, controls mechanical behavior, likes the pore water pressure. Oh, nice, we are talking about the same. And then you have the first definition. Suction is defined as the free energy state of soil water. It can be measured in terms of the partial vapor pressure of the soil via that equation. Strange, right? So as soon as we are desaturating a little bit, we are entering the exoteric world of thermodynamics. But that's not finished. Second, you are hearing about metric and osmotic suction. Take a breath and come with me. Metric or capillary component of free energy. In suction terms, it is the equivalent suction derived from the measurement of the partial pressure of water vapor in equilibrium with the soil water residing in the soil relative to the partial pressure of water vapor in equilibrium with the solution identical in composition with the soil water. I'm saving you for the second. You are saying, no, this not me. I'm never going for it. Finally, at some point, you read and you say, oh, in practical terms, that's the difference between air and water pressure. So the ground thermodynamical definition, poof, disappearing. So what? Let's clear the ground first, immediately. Pore water pressure is defined exactly in the same way in saturated and unsaturated. There is one difference, and the difference is that in unsaturated the pressure is negative, and then is more difficult to measure. Because it is difficult to measure, we have devised indirect techniques, and this is where you need the thermodynamics to interpret the technique, but that's clearly another story. If instruments to measure the negative pore water pressure were invented since the early days, you would have never defined the suction thermodynamically. You would have never talked about metric and osmotic. You would have even talked about difference between air and water pressure, because we are always dealing with gauge pressures. So the moral of the story, forget about thermodynamics, metric and osmotic suction, unless you are concerned with the measurement, but it's not the topic that you are dealing with at undergraduate level. And simply, we introduced something that is named suction. By convenience, is the opposite of the pore water pressure in order to deal with the positive variable. Then you go to the effective stresses. That's a non-comprehensive list of effective stresses. Oh, the first reaction of a saturated teacher, we are violating the principle of effective stress. Oh, mess here. Okay, let's dismantle the principle of effective stress. That's the original definition by Terzaghi. The key word here is measurable. So the effective stress is not a principle, is not a theory, is an experimental observation, like the first and second principle of thermodynamics. So why, depending on the measurable effect we are looking at, we are choosing the effective stress of convenience depending on what we are looking at. I'm going to talk here about shear strength and stability, and this is what I'm selecting. Nuria is going to talk about wet-induced collapse, and this is what she is going to use. Is terrible? No, because even in the saturated soil, you have cases where the effective stress that we use does not work. For example, if you have the stiffness of the matrix is comparable with the stiffness of the grain, our effective stress is not working, so there's nothing new here. Then why teaching unsaturated? You have also papers that are coming after somehow attacking the problem in this way. So you always have soil above either the groundwater table or the phreatic surface. Above the phreatic surface, you have two things. Pore water pressure is negative, and then the degree of saturation is generally lower than unity. Now, what I've been taught, and what I still see teaching, is that above the groundwater table, we are assuming the pore water pressure 0. So we are forgetting that it's negative, and we take it 0. 0 pressure is what we would have in an ideally dry soil. That's why I'm calling it dry assumption. The rationale is simple. The negative pressure has a positive contribution to shear strength. If you are neglecting it, that's a conservative. Good. Let's go on. Maybe, yes and no. It leads to excessively conservative design. No one cared in the past, but now it's carbon consuming. So maybe have a thought about that. Forget about the climate interaction. So everybody's talking about climate change in geotechnics. If you don't have the unsaturated, no way. You may have faulty design. I will show you an example. And sorry, coming straight from lecture yesterday, you cannot understand compaction because the compacted soil is unsaturated. Excessively conservative design. No, you cannot build a sandcastle. That's a sandcastle, is above the groundwater table. So what we do, 0 pressure, right? So you have the more circle in terms of total stress coincides with the one in effective stress. No way. So if you are a geotechnical parent, nail sandcastles, carbon footprint, lime stabilized sandcastle, geotextile, Jorge will be happy. And you know the story, of course. So excessively conservative can be carbon expensive. So something to have a thought about. Okay, forget about the sandcastle. That's an excavation. Same story. So if you're doing your calculation with a dry approach, you are going to say, oh, this excavation is not going to stand up. We need to build returning structure. And that's the problem. Your contractor is laughing at you. Who is this blood engineer? That slope is a cohesionless material. It was there for decades. Why they're asking me to build a retaining wall? Climate interaction, briefly. You have water in because of rainfall. You have water out because of evapotranspiration. If you have a problem of slope stability, you have that green portion that is above the groundwater table. When you have a rainfall, you are moving the pressures from very negative to less negative values. The degree of saturation is increasing and it is failing. Now, these are two examples in UK, but you have billions of rainfall-induced landslides on Google. Or the other way around, drought-induced building damage. is a huge problem in UK and France, quantified economically, but you have problems everywhere. The story is simple. You have evaporation, the soil is shrinking, you have the settlement of the peripheral foundations, you have differential settlements, and the walls are cracking. Italy, France, UK. So at some point, we need to go there if you want to put the climate in. Faulty design. Still back to that vertical cut. You are doing the calculation and say, according to my calculation, that vertical cut cannot be stable. Then you go to the field, oh, not bloody stable, this one here. So at this point, you are challenging yourself, and how can I reconcile my calculation with what I'm observing here? Consider that the problem is not only a design forward, sometimes we go design by back analysis first. Now, if you know the story, you will realize that the pressure is negative. This is creating a positive effective stress. So the effective stress, if you know the story, is sitting there. Perfect explanation of why it is stable. If you don't know about that, and the only tool is the one that you see, the only way to make it stable is to put a cohesion there as a soil parameter, so a cohesion that is never cancelled by anybody in the world. And you see, when you are nobody confessor, when you go to a consulting company, or even if you are playing with model, oh, put a little bit of cohesion, but how much? 1 or 2, but why 1 or 2? Well, a small number, that's fine. Now, it's not only the reason, the partial saturation, I know, but. So, a cohesion invented means that becomes a soil parameter, but of course, if you have a rainfall, that additional term is going to vanish. But this is one example of excavation that was failing because of rainfall. What is convenient to start with? When we are leaving the soil mechanics and we are moving to geotechnical engineering, this is what we deal with. We are never starting from the serviceability. We are starting from the ultimate state for 2 reasons. First, because it's the first box that you need to tick. Second, most of the cases we can deal with by just looking at the shear strength. And this is what we do at the undergraduate level, and I think this is what everybody does as a first step. Then, in advanced courses, we are making things more complicated. So this is what I'm doing here. So you have an hydraulic problem, you have a mechanical problem. We know they are coupled. If you want to know about the coupling, go to the later lecture. But what I'm doing here, I'm uncoupling it. Technically speaking, I'm considering a rigid, perfectly plastic material. And this is what we consider, or what we already do at the undergraduate level when we start about ultimate limit state design. In this exercise, I'm considering the simplest hydraulic flow, hydrostatic. But I don't have time here. In the class, we are also dealing with the transient. So essentially, what you need to talk about is quantifying the shear strength that develops along the failure surface. I'm anticipating where I'm going to. That's the failure criterion. So we need to develop a failure criterion for the unsaturated soil. And then you are going to discover that in the failure criterion, you have 2 things. You have suction, or the negative pore water pressure, and the degree of saturation. So at some point, you need to understand what happens in terms of relationship between suction and degree of saturation, and that's what we name water retention behavior. How do we teach those 2 components here? So we have 3 design. This is our experience. So I'm not saying that this is what everybody has to do. I don't know, you do whatever you wish if you want to do it, but this is what we do. Non-axiomatic fashion, so we are not fitting mathematical models on experimental data. We are doing the other way around. We are developing mathematical models derived from elementary physical mechanisms. Second, we go for elementary physical mechanisms because we want students to develop a bottom-up understanding. Third, we provide real-time, small-scale experiments for 2 reasons. One is to have a visual deformation, a visual demonstration in the class, also as a way to engage the student. But most of all, it is impossible to add an experimental component in unsaturated soil mechanics because most of the research laboratories, they do not have the equipment. Forget about the teaching laboratory. So if you want to put the experimental component, we need to find another way, or we found another way. And because I'm talking about slope stability and demonstration, let's look at this very nice exercise. So that's a slide. This one is charged with dry sand. We know the slope stability. We know that that should fail when the friction angle, so when the inclination reaches the friction angle. So be patient. We are going to raise, to incline the slide. Now, the perspective is not helping, but that's me measuring, so to demonstrate that we actually measure the inclination of the slide. And it was 32, 33 degrees, but we were matching the number that we were expecting. Perfect. So we have a good understanding of the dry soil. Now, that's an unsaturated. So the same slide filled with an unsaturated sand. First of all, if you were designing it with the dry approach, you would say at 33 degrees it should fail. Okay, but we know that it should stay higher, right? So if I'm telling you that you can incline a bit more, you're not going to be surprised. But you're going to be surprised by how much we can incline that slide as an easy, straightforward demonstration on what the suction does. There is a trick here, but the trick is not in the experiment. There is a conceptual trick here, but I will tell you later in case. The reason for that experiment, because we did the calculation, I said, no, it cannot be 90 degrees. It was 90 degrees. So water retention behavior. First, air-water interface. So the separation between the air and water behaves like a membrane in tension subjected to a uniform stress that we name surface tension. That's an example from nature, but difficult to reproduce in the lab. This is something that you can do in the lab. So this is a paper clip that is floating on water. And the reason why it is floating is that the membrane is bending, and the surface tension is generating a vertical component that is counterbalancing the weight. It's really surface tension, because if you put it down, of course, it is going to sink, because the density of the iron is much higher than the density of the water. Second story, what happens to that interface when you are in contact with the solid surface? Because of the adhesion forces, you are bending in this way. So that's a drop of water in a capillary tube, not a microscopic, so this is almost 1 millimeter diameter. And you see that the interface is curved. What if you put those things together, and then we are starting from an example we are all familiar with, possibly even from high school, that is the capillary rise. So we focus on that meniscus. Now we have everything that we need for a mechanical equilibrium, because you have the water pressure from below, we have the air pressure from above, and then we have the surface tension. And then we have the angle that is inclining the surface tension at the junction. If you go for that equilibrium, you will discover that the water pressure is lower than the air pressure. You see that the red is smaller than the blue. And that number is controlled by the surface tension, but also the diameter of the capillary tube. Now, mathematics, but you can also describe that without the mathematics. So you have a pressure on the convex side. You have a pressure on the concave side. The pressure on the convex is lower. Sorry, I'm teaching in October, so that's Halloween time. So the balloon is telling us exactly the same story. Then the same equation is telling us that the capillary rise is inversely proportional to the diameter. This is a Petri dish with a little bit of water, 2 pipettes put into it, and you see 2 different levels that you have there. Something that you can get without the example, but the example is making a difference. And then the water retention. So imagine that you have a capillary tube on the left, and then you have a reservoir on the right. If the tube was prolonged, you will see a capillary rise, but I have decided to cut the tube. So at the top of the capillary tube, the pressure is the one imposed by the reservoir, that is 0. Now, let's imagine that you are lowering the reservoir, so you are generating some negative pressures. The system may remain in equilibrium. Of course, in order to remain in equilibrium, at the top you need to have a negative pressure, but this can be accommodated by the meniscus that is bending. But if you move it further, at some point, the meniscus can say, I cannot bend anymore to accommodate that pressure, so I need to go down. So I'm moving down in order to maintain the capillary rise at the same level. Look at that transition here. So that's the transition where you have the meniscus that is receding in the capillary tube. So this is technically air entry because the air is entering the capillary tube. And this process here is controlled by the minimum pressure that the meniscus can sustain. And this is controlled in turn by that equation. Now, we are engineers, so qualitative is not enough. We need to juggle orders of magnitude because our qualitative understanding is passing through orders of magnitude. Orders of magnitude. Dimension of the grain, sand, silt, and clay, dimension of the pore, 1/6 of the diameter of the grain. The air entry suction is 10, 100, and 1,000 kPa when moving from sand, cinder, clay. So we should expect that when the suction goes to 10, the sand is starting desaturating, so you have the air entry, and then 100 and 1,000 for the clay. Let's keep this number in mind, and let's move on. But now the soil is a very complex porous system, so the best way of mimicking the complex porous system in a soil is to have a system of capillary tubes of different size. So the one is everything is saturated. Now, I'm lowering in point 2 the reservoir, so I'm imposing a negative pressure at the base of the system of capillary tubes. The big one is going to empty. The other ones are still fine because you can maintain the negative pressure. And then you go to 3, the second is going to empty. You are going to 4, and the third is going to empty. Oh, let's put together. On the horizontal axis, the negative pressure that we are imposing at the base of the capillary system. And let's put on the vertical axis the degree of saturation of the system of capillary tubes. Initially, everything is saturated. Then the first is emptying, the second is emptying, the third is emptying. That's the air entry. So what happens if you have a clay, if you have a silt, and if you have a sand? Oh, of course, you don't know, you need to measure it. But if you want to have an order of magnitude without touching the soil yet, I use those tools in order to quantify the order of magnitude that we're expecting for 2 reasons. To have a physical understanding. Second, I can provide experimental data to the students. And who is bloody going to say if those experimental data are making sense or not? You need an independent, simple, conceptual tool in order to do a data quality check of the experimental data that are produced by any laboratory. Even more, imagine that instead of having different diameters, you have all capillary tubes of the same size. So you are emptying all of them at the same time. So you are going to have the dust curve. So you are going to discover another thing, that the behavior of the degree of saturation beyond the entry value is controlled by how uniform or how well graded are, in this case, the size of the capillary tubes. In the real world, we are talking about how well graded are either the pore size or essentially the drain size. So what happens before depends on what is associated, is controlled by the grain size distribution. Shear strength. If you take a picture of the soil, you will find the water in 2 states. Either the water is forming menisci at the interparticle contact. We name that water meniscus water, and this is a meniscus contact. Or we identify sub-regions that are fully saturated. And clearly, if you take a snapshot of a contact, you will see that the contact is fully occupied by water. So we name that water bulk water, and that contact a saturated contact. Now, let's look at the saturated contact first. Equilibrium. Let's look at the intergranular force N, or intergranular stress. You have the total stress at the bottom, you have the intergranular force at the top, and then you have the pore water pressure. If you are doing an equilibrium, you are discovering that the intergranular stress is equal to either the total stress minus the pore water pressure, or the total stress plus the suction, just changing the sign here. Now, let's continue by making the assumption that intergranular stress is equal to the effective stress. Please, I'm saying, That's entirely wrong. That's a bad, bad assumption. But that's why I'm saying Bishop and Scampton, forgive me. But if you want to have a Wikipedia lecture, not you, but the students as well, I need to take a shortcut. So that's a bad assumption, but it's very convenient. Let's see what happens at the meniscus contact. Now the shape of the air-water interface is a bit more complicated. You have two radii of curvature, C and B. The two radii of curvature are both contributing to generate the suction in the water. And those two radii of curvature are depending on the radius R of the spherical particle and the angle B that is defining the position of the junction of the air-water interface. And let's go for the equilibrium. So you have clearly a component associated with the total stress, and then you have two components associated with the presence of the meniscus. Is the negative pressure in blue multiplied by the area where the blue water is, plus the surface tension along the perimeter. So both components are contributing in the same way by creating a compression to the grain. So the surface tension and the negative pressure are increasing the intergranular stress. Example in the lab. So that's a glass bead. Now the picture is difficult because everything was transparent, but there is a Petri dish here. So that's a Petri dish, and then you have a glass bead that is hanging from the bottom of the Petri dish because of the meniscus water. Okay, let's now connect first the bulk water and the meniscus water on the water retention curve. In the first range, before, when the system is saturated, you have bulk water everywhere. So not only a sub-region is saturated, everywhere is saturated. Then you have the region 2, when you have both bulk water and meniscus water. Then you go to region 3, when everything is becoming meniscus. And being forgiven by Scampton and Bishop, let us assume that the shear strength is the intergranular stress, multiply the tangent of the friction angle. So of course you have one component of the intergranular stress that is coming from the total stress, I'm taking it out, plus a component of the intergranular stress that is associated with the suction. Let's see what happens here. When you are in this case here, bulk water everywhere, the intergranular stress is exactly equal to the suction. Oh, not surprised, the soil is still saturated, so we need to recover the effective stress here. When you are here, you have the intergranular stress that is actually associated with the meniscus water and the bulk water. But at relatively high degrees of saturation, the component of the bulk water is dominating the one on the meniscus. So as a first approximation, we can say that the intergranular stress associated with suction is only due to the bulk water, which means suction multiply the fraction of the volume occupied by the bulk water divided the total volume of the pores. And this is roughly equal to the degree of saturation. So suction times degree of saturation. Then you are entering that stage here. You can demonstrate easily, quite easily mathematically, that when you are at that stage, even if you are changing the suction in the meniscus because you are changing the configuration of the meniscus, the intergranular force is not changing much. For one simple reason, because when the suction increases, the meniscus has to retrace towards the contact point, and the contact area is decreasing roughly. So this is the case when the intergranular stress is constant in the sense that it is independent of suction. And now we can combine the two. So the shear strength on the vertical axis, the suction on the horizontal axis. When the suction is 0, there is only the component associated with the total stress. Then below the re-entry suction, I'm following the effective stress. So you see that you follow the slope incline of phi prime. Then you are entering the range where suction times the degree of saturation is controlling the process. So you have a decline until you are reaching a stage where the shear strength levels off, and this is where all the menisci are acting at the interparticle contact, and the intergranular stress, and therefore the shear strength, is not changing any longer with the increase of suction. Good. We are ready now to go. So if you have an hydrostatic pressure, you know the suction, or if you have a transient flow separately, which I'm not addressing here, you need to solve a water flow problem. Once you have the suction, you enter the water retention curve that you have defined and you quantify the degree of saturation. At any point in the slope here, you can rewrite the Bishop method by simply plugging the shear strength that is coming from that calculation. I'm not going on in the sense that the easiest part, because now I'm speaking really the same language of the saturated what we do, but the exercise is fully developed in the paper. How much time do I have?
5 minutes.
Oh, okay. No, I'm already at the end. Now, sorry, yesterday I was looking at the compaction story. Oh, the bloody, the compacted soil is an unsaturated soil. You cannot compact the soil if the soil is not unsaturated. Sorry, it's not about marina. We are teaching compaction in the first year, and my bad, no one has ever told anyone that in order to understand compaction, we need to get the unsaturated. So before marina is my bad, because I've never talked with the teacher in the first year, oh, bloody, that's an answer. How can you explain the compaction without talking about unsaturation, partial saturation? Okay, so 2 questions here. How you have a bell shape? So the compaction goes this way. So there is a maximum. Why this is happening? Second, if you have scrutinized billions of compaction curves, you are going to discover that that optimum is almost always lying on 80–85%. That's strange, right? So there might be a reason for that. When you have sands, when you have clay, all the curves that Marina was showing yesterday. Okay, let's shift to the unsaturated now. 80% means here, so you are sitting on that part of the curve. So the blue one, when you are on the dry of optimum, you are at low degree of saturation, so you are on the blue branch of the water retention. When you are wet of optimum, you are on the red branch of the water retention. Where is the difference? On the blue branch, you have the meniscus water, the bulk water, but the water phase is continuous. So if you're sitting on a point at the top, you can follow a path through the air and go to the bottom. Whereas when you are on the red part, when it is saturated, but when the degree of saturation is relatively high, the air is discontinuous. So the air is present, if you wish, in form of occluded cavities. So let's revisit that compaction by see what is the consequence on the mechanism of densification of the material. If you have a continuous air phase, you are reducing the volume by expelling air, because the air can go out, because the air is continuous. But where you are on the wet of optimum, you need to expel the water, not the air, because the air is occluded. So you need to chase the water out. So the mechanisms by which the soil becomes denser are entirely different in terms of pore fluid that needs to be displaced. What happens here? You have all menisci here. The degree of saturation is low. So those menisci are generating a pressure. So you are increasing the intergranular stress. You are increasing the shearing resistance at the contact. You are preventing the sliding at the interparticle contact. So you are maintaining an open structure, low density. When you are increasing the water, you are taking some of those menisci, they are going away, as if there was a cement at the interparticle contact, and then you are killing it. So those particles that were prevented to slip against each other are now slipping, and then you are getting a density. Up to a point. This is the point when the air becomes occluded. So now the mechanism is different. The air is very easy to chase. You compact, the air is the permeability of air is very high, so the air is moving so fast that you're not even thinking that there is a consolidation process. Technically there is, because the air is taking some time to flow out, but it's so fast that you don't think about it. Now you need to chase the water. Now, forget about this. Imagine that you have an odometer sample, laterally constrained, fully saturated. You are loading it, and you have no drainage. You are never going to compress the sample. That's the reason why, when you are loading an odometer sample, you have a build-up of pore water pressure, because the sample cannot deform. Now, we are not exactly in that range where the soil is fully saturated, but we are very close by. So the reason why it is becoming more and more complicated is that you need to chase the water. So when close to the optimum, on the wet side, probably there is a mix of compression of air bubbles. Virtually, when the soil becomes saturated, no way of compressing it. And we know about, because we all think about dynamic compaction. This is what we do in the lab. Dynamic is a sort of bearing capacity, so you are not applying the load on the entire surface. You are applying the load centrally, and then you have the soil that is bulging like the bearing capacity. But, for example, the wet branch cannot be achieved if you are doing like the odometer. If you are compacting statically by applying a uniform stress, the wet branch does not exist, because you cannot, so you go horizontal because you cannot compress. Moral of the story. Can we teach elements of unsaturated soil at undergraduate level? Yes, we think we can. So I think I'm 30 minutes, right? No, I'm finished. Now I say that my lecture was taking 30 minutes. Now, if you were students, I will go at slower pace. I will probably finalize the stability analysis, but it's almost trivial. So this means that it's a 2 hours lecture. Okay, doable. If you take another 2 hours, so the next lecture, you can introduce the hydraulic conductivity still using the capillary tubes, and then you can represent the water flow in this way here. So that's not a consolidation. So that's not the excess pressure dissipation that you will see in the saturated. What you see here is at the bottom a water table, at the top ponded infiltration. The red curve is the initial hydrostatic condition, and what you see is the evolution of the pore water pressure as the infiltration proceeds. If you want to know more, it is here. One last comment. Can we teach unsaturated soil mechanics in 4 hours? Are the students able to solve the problem in 4 hours? Trivial answer, of course not. But that's not our first point. The first point for the students and the future engineers, first is being aware of the problem before deciding, oh, I need to find a way to solve it, either myself or I'm asking a specialist. So if you are an unsaturated person, you will realize how many simplifications I've introduced here. That's, of course, a price to pay. But everything, I didn't tell you all the truth, but everything I told you was the truth. So I was not lacking rigor in that. And I'm stopping here.
I like very much all the lectures and all the presentations today and yesterday. So I want to give congratulations for all the committee members. But for Alessandro, actually, I like very much what you present. But I also want to suggest you change the name of the compaction curve, because it's not a bell shape. Because I mentioned that the bell is something like that. Because of the bubbles, you're right, we are not able to reach the saturation line. So we have a restriction after the maximal point. Do you see? That's the reason I was planning to use, because I did a presentation with 9 slides. So I was planning to draw a compaction curve and show that's not a bell. Because of that, do you see? And it's much easier to draw the compaction, because the compaction curve, it's an experimental curve. So it's always, we have error during the measurements. But the saturation lines are theoretical lines. And we teach the students, when we start to teaching the index properties, we are able to draw the saturation lines. And also the saturation lines, they are parallel, the partial saturation lines, they are parallel to the full saturation line. And that's the reason, because it's not exactly 80% the maximum. For example, for situ material, you have around 7% maybe. But after that, you have the occlusion, you're right. So, and that's when you do the compaction, we are not able to eliminate the occlusion air. That's the reason, because our limitation, we don't have room for going to a bell shape. Do you understand what I'm saying? And it helps a lot because, for example, you have maybe 4 or 5 experimental points from the lab, the compaction test. And in that case, do you see, it's helped a lot. For example, I am not a good drawer, but I was planning to draw in the, I was asking Adele if I could do that. Because it's much easier for me when I draw the saturation line, because I know that when I'm wetting sides of the compaction curve, I am close to the saturation. So I don't have room for reach the saturation because the bubbles. I am not able to eliminate the bubbles when I'm doing the compaction work. Do you see? That's the reason, because you're right. We don't need a new class for unsaturated soil for show the students. But do you know, that's the reason, because I think that's not a bell. It's only a small comment. Maybe I talked too much.
3/4 of the answer is a research answer, which I'm not answering here. I was not saying that you are reaching saturation. I was trying to provide a simple conceptual model to explain why you go down again. So I'm not saying that you are reaching saturation. So I'm saying a conceptual reason why you're going down again. The conceptual is very simple, because I can tell you probably 3, 4, 5 reasons about what's happening here, including, that's becoming a research story. So the point is, should we tell the students, this is what we see, and this is what we see, end of the story, right? At this point, you don't need a teacher. You go to Wikipedia, you see the bell, and that's the compaction curve. Or we try to provide some conceptual tools in order to have a clue, or half of a clue, or a quarter of a clue about what's happening. So that's the purpose of that discussion. This is one story. The second story is that when you are compacting, now I'm looking at the practical side of the experiment that you do in the lab. You take a powder, you spray it with water, then you prepare a wet powder, you put in the mold and you compact. Now, of course, you cannot reach saturation, because take a clay. The clay, not by chance, there is a reason for that, the clay is saturated at the plastic limit. Try to mix a soil at the plastic limit, you can, it's so sticky. So you are never reaching saturation because you are never preparing a saturated sample. But that would be another story. So that's my fight. Now, there are few unsaturated people here. That's my fight with the unsaturated community. And that's the barrier that we have created with the teaching. Of course, I can tell you, I can sit on the other side, I can say all what I was saying wrong about that picture of the compaction curve. I can tell you 10 reasons why that's wrong. And that is exactly the point why I'm trying to understand, I provide a simple explanation, and then the unsaturated, no, it's more complicated. So imagine, let's look at this side here. Who is teaching as a first approach in geotechnical engineering slope stability using the limit equilibrium and the cohesion and the friction? This is the first thing that I'm teaching, right? Right. Okay, the limit equilibrium means that we are assuming rigid, perfectly plastic with associated flow. Technically speaking, what we are doing. Now, we can spend 3 days of conference, say that the soil is not rigid, is not perfectly plastic, is not associated flow. But that's not the point. That's not the point. So we are not starting teaching the students say, no, the soil is more complicated. We are never going for the teaching. So let's start from the base so that I understand what you're saying and I have a list. So the attempt there was, if I'm successful.
Alessandro,
Okay.
come here. No, no, no.
I have a question.
No, come here, come here.
Continue.
Meaning,
No, but I'm not.
I was told indeed, good, I didn't think about it. You should talk to everybody by looking at it. Yeah. And then we have something. You know, you can go, you can finish.
No, I finished. No, I'm talking too much.
No, I was wondering whether, Charles, is it about compaction or not?
No, it's just...
No, because if it's about compaction, I would like to have if somebody wants to say something about this particular topic, given that yesterday Marina was saying, you know, alpha ranking, then I'll come back to you.
About compaction. That I remember when I was a student of the master and in the PhD that even having courses about compaction or classes in detail, I remember that there was I found missing, or there was a gap relating the variables used in practice in Proctor with the theory used in soil mechanics, like normal consolidation line. There is a gap when we talk about compaction and when we talk about the modeling of the rest of the soils. And then, in my experience in our courses or in my courses in the master, I introduced this explanation or this to jump from the Proctor plane to other variables that we use to model the initial conditions in practice. Because at the end, if they have to model a dam, for instance, they have to move from the initial conditions in practice with the dry density and the humidity to pre-consolidation to define the position of the LC and the suction with the water retention curve. And I think that it's an important point when we finish all of these concepts in compacted soils to make an explanation how to make together all of these concepts with the rest of concepts explained in the rest of the course, like the consolidation line.
Can I make a point on my side? Now, clearly there is a very, very partial view, but the merit of that discussion is, of course, now you need to touch this. So now no one is going to be surprised anymore if at some point, if you want to understand more, you need to turn to unsaturated soil mechanics, to the unsaturated class. So the explanation in terms of partial saturation, limited, and all the rest, and also the applicability of the Proctor, whatever you're thinking, but that's switching on a light and say, if I want to understand more, what should I do? Should I read more books, or maybe I should attend your class because there's an unsaturated story? Hopefully, this way is to switch on a light and say, okay, I'm attending that class because there is an unsaturated story if I want to understand more.
No, but this is a previous point. It's just that this compacted soil, this you can represent the behavior of the compacted soil also in a stress path plotted in a typical plot.
Would you teach in the first year?
Sorry,
but would you teach that in the first year? Because my students are coming the first year, and in order to familiarize with the soil as everybody else, they're doing the plastic cleaning, they're doing the compaction. That's my point.
Yeah.
I published the model. I published a model on the compaction and the constitutive model during the compaction, so I understand where we are. But what are you doing with the first year when you are teaching the plastic limit? That's my point. Either we are saying, from now on, we are taking out all the pages in all geotechnical books when they are talking about compaction, and then we are forcing all the universities to remove the compaction curve, I would agree. Or, if you are keeping it there, how we are reconciling the two?
Yes. I don't know, Alessandro, in Italy, your education, but my education, I was asking Francesca, We are not having compaction when we do soil mechanics, and I'm not teaching compaction when I'm doing basic soil mechanics. I don't know if it's an Italian tradition. It's something that I was exposed to by chance, but you know, that's why, you know, like in some countries, and also maybe the position of this chapter or this discussion in some books, in some countries, indeed it's a sort of a practical way of doing things that doesn't have the dignity to become something simple for, you know, at the very beginning, and then it will come when you will have on that side. Anyway, that's another story.
There is a chapter on compaction in Lambert-Whitman. Eh? Yes, but there is a chapter on compaction in Lambert-Whitman, so no, 69. So I'm just saying that.
I know, but that's, again, at the end of the book, and the Italian practice, like...
if you are asking me, should we keep it or take it out, I'm telling you...
Anything else on soil compaction? Because it's, no, on this discussion, really. And then, if you allow, another question from Charles, and then we can close it. No, compaction, Charles.
So, there's a geotechnical textbook by, now I can't remember his name, but it's a very philosophical book about geotechnical engineering, and basically it says in it, it's very similar to the Pareto effect, that like 80% of geotechnical behavior can be explained with a few number of parameters. And then to get to 100%, you have to introduce 80 or 8 more parameters. So you need to almost triple the number of parameters that you need to take into consideration. And I think that's almost what we're seeing with, like most geotechnical behavior, we can explain with a small set of variables. And as soon as we want to start incorporating the unsaturated aspect, we have to incorporate a whole lot more parameters, and then there's a whole lot more debate, as we're witnessing here. And I think, like, there needs to be some, if we want to incorporate another parameter, we need to be very careful how many more we do incorporate, and at what benefit that is going to be to the behavior that we can explain, especially at the undergraduate level. And I think such an animated debate is probably quite off-putting for a number of lecturers who want to actually go into this field, because we get completely, if the experts can't agree, then...
I don't know what you have in mind, but if by any chance you are thinking why to move from saturated soil to unsaturated, we need to add more parameters, if by any chance you have that in mind, my answer is, why we are all thinking that unsaturated soil are a special case of saturated. So we all think that the saturated is the reference, and the unsaturated is a special case of it. Of course, it is the other way around, because the soil is unsaturated, and the saturated is a special case. So you should not complain if when we move to the saturated, unsaturated, we are adding more parameters. You should complain if, when moving from the unsaturated to the saturated, we are not cutting down parameters. Because to the saturated, we are simplifying the story. So we are going to a simpler case. You have 0, 100%. The dry soil, forget, does not exist in nature, except the sand dune, but the dry soil does not exist. You have 100%, and you have all the rest. So the saturated is a very, historically, is occupied 90%, but the saturated is a very special case of the unsaturated soil. So we are not adding parameters. We are so lucky that for life we were looking at the very special case. And of course, if you have a very special case, you can cut it down. Am I passing the message?
You pass the message. Any other final? Okay, Francesca, and then we close it with...
To add a consideration that one thing that I see my students struggling, because they have in mind this duality, dry or saturated, with nothing in between. When sometimes I ask them to calculate like, you know, stress, total stress with depth, for the soil above water, they use dry uniweight. And they are convinced of that.
Because
Yes.
we are missing that point.
So-
we are not assuming the soil to be dry. We are assuming the soil to have not negative but zero pressure, as if an ideal dry soil that does not exist in nature except the sand dune was ideally dry.
So
I know what you're saying, I know, and my
This
students
sometimes
in the other classes are
happens.
doing the same.
sometimes after, and I ask them, why did you use the dry soil? Because we
Because
are
we
above
tell them that
water,
the soil
pressure
is-
is zero.
Because we tell them that the soil is dry when calculating the effective stress. That's our mistake.
Yes.
We should tell them to calculate the effective stress, we are making the assumption that the pore pressure is zero, which has nothing to do with the dry soil.
These I thank you, everybody, unless there is something.
No, I have a
very-
deal a public deal to Talia. Where is Talia?
What is it?
Talia, the last presentation, right. I'm doing exactly what you are doing. So I'm taking an ideal slope and I'm doing my calculation, etc. If by any chance, one of the three companies that was replying, that they say, we want to know more about how the suction is reinforcing or stabilizing the slope, they are coming up with the quarter of a case study, I'm happy to jump on board. And next time, you and me, instead of developing an ideal slope, preparing a case inspired by the problem that they have. I don't want to have anything except a grain size distribution at least. And if it is a clay soil, a plastic limit, and then we can move from there. I'm not asking to have a full set of experimental tests with all saturated and unsaturated parameters. If by any chance, because you were so lucky that we are replying.
Okay, so you have a project for the future, and if any company wants to jump on board, the team is done. Thank you very much. We have a break.